Okay, in this lecture we're going to start our Chapter 1 material on parametric equations and polar coordinates. And in section 1.1, we will talk about specifically parametric equations. So parametric equations are going to be used to describe curves in the plane, which may not be the graph of a function. So, for instance, we might consider an object moving through the plane or through two dimensions over time, and the path that it traces out, or the path of our object through the plane, may not be a curve which is the graph of a function. So, in some of the examples that we've considered in Calculus 1 or 2, we're looking at the graph of some function of the form y equals f of x. But we know that not every plane curve is the graph of a function. In particular, if a curve does not pass the vertical line test, then it is not the graph of a function. So how can we describe these sort of curves? So one way is to make use of something called a parametric equation. So let's get a definition. So let's say if x and y are continuous functions of a variable t on some interval, let's call it capital I, then the equations x equals x of t and y equals y of t are called parametric equations, where we call the variable t a parameter. So the set of all points xy, where x is given by the x of t equation and y is given by the function y of t, as t varies over the interval I, is called a parametric curve. So it's the set of all points defined by these equations x of t and y of t. So as an example, let's say in the plane, maybe the first quadrant of the xy plane, we have some curve that maybe looks something like this. And we start at some initial point. So our starting value is called an initial point, and we might have some ending point, which would be called a terminal point, as the values of t range over some interval I. So let's say, for instance, if our interval I is some t interval, let's say from A to B, then this initial point would correspond to the value t equals a, and our terminal point would correspond to the last value of t equals b. And when we're sketching a parametric curve, we might include little arrows along the curve, which indicate the direction of motion along this curve. Or what we would call the orientation of our curve. Are we moving from left to right, right to left, or in which direction as t is increasing? So we can see for this curve that I sketched out, certainly it is not the graph of a function because it doesn't pass the vertical line test. However, we could describe that curve by using parametric equations. So now that we have a definition of parametric equations or a parametric curve, let's look at some examples of sketching parametric curves. And we'll see a couple of different techniques. So in this first example, we are asked to sketch the curves described by the given parametric equations, and we're supposed to use arrows to indicate the orientation of this curve. So we've got two parts here. In part A, we have the parametric equations x of t is equal to t minus 2, and y of t is 2t minus 1, as t ranges from 0 to 4. So there's a couple of ways we could go about sketching this curve. Let me zoom in a little bit here. One way that we could go about sketching this curve is to substitute the values for t within this interval into our parametric equations for x and y and see what we get, what points would lie on this curve. So let's consider using a table of values here. So we're going to choose t values within the interval from 0 to 4 and find the corresponding x and y values. So let's take a look here. Our t values are ranging from 0 to 4. So let's maybe choose integer values for t, 0, 1, 2, 3, and 4. And then we're going to find the corresponding x and y values. So let's start with t equals to 0. If t is equal to 0, then x would be negative 2, since x is t minus 2, and y would be negative 1. Now, if t is equal to 1, x is negative 1, and y is then positive 1. If t is equal to 2, x is 0, and y would be 3. If t is 3, we see that x would be 1, and y would be 5. And then if t is 4, we have x is equal to 2, and y would be 8 minus 1 is 7. So let's plot these corresponding points on the grid that we're given. So for t equals to 0, our first point was negative 2, negative 1. So this is the value corresponding to t equals to 0. Now when t is equal to 1, we had the point negative 1, positive 1 for xy. When t was equal to 2, we had the point 0, 3. When t was equal to 3, we had the point 1, 5. And when t was equal to 2, or excuse me, when t was equal to 4, we had the point 2, 7. So this was our value t equals to 4. So the curve, which is described by these equations, would be the curve passing through these points. And we can see that it looks to be a line segment here. Now we're supposed to use arrows to indicate the orientation of this curve. So as t is increasing from 0 to 4, we saw that we were moving from left to right along this line segment. So let's look at another example. In part B, we've got the parametric equations. X is 3t plus 2, and y is t squared minus 1, as t ranges from negative 3 to positive 2. So again, let's use this same approach of taking values of t within our interval and substituting them into the parametric equations to find points on our curve. So here we could start with a table of values for t, x, and y. Now t ranges from negative 3 to positive 2. That's our interval here. So let's choose integer values for t within that interval, starting with negative 3, negative 2, negative 1, 0, 1, and 2. And we're going to find the corresponding x and y values for the t values in our interval. So if t is equal to negative 3, we see x would be negative 9 plus 2, or negative 7. And then y, when t is negative 3, would be 9 minus 1, or 8. Then when t is negative 2, we would have negative 6 plus 2, or negative 4 for x. And y would be 4 minus 1, or 3. When t is negative 1, we see that x is negative 1. and y would be 0. If t is 0, x is 2, y is -1. If t is 1, we have 5 and 0. And if t is 2, we have 8, excuse me. Oh yes, 8, and then if t is 2, let's see, y is 3. So let's substitute or plot the points that we found for x and y on our grid here. So starting with t equals to -3, we had an x value of -7, +8. So this was our initial point corresponding to our starting value of t, which was -3. Then when t was -2, we had the point -4, 3. When t was -1, we had the point -1, 0. Let me clean up my earlier work. When t is 0, we had the point 2, -1. When t was 1, we had the point 5 and 0. And when t was 2, we had the point 8, 3. All right. So connecting these points, we have a curve that looks something like this. It's in fact part of a parabola. And using arrows to indicate the orientation of this curve, what we see as t was increasing from -3 to 2, we were moving from left to right along this curve. So in this first example, we see one way to plot parametric equations or a parametric curve is by choosing specific values of t in some interval, finding the corresponding x and y coordinates for a point on the curve, plotting those points, and then connecting the dots. But we see, of course, that this is not a very efficient method for plotting parametric curves. It's a little time-consuming, and if we have parametric equations which are a little more complicated, maybe involving exponential functions, trig functions, or log functions, well, it's not very easy to evaluate the specific values for x and y unless we're making use of a calculator. So let's consider an alternative approach here. What is another way that we could go about plotting these parametric curves? So another way that we can try to sketch a parametric curve is by trying to eliminate the parameter and obtain a Cartesian or rectangular equation. So I'll mention here, in order to obtain the graph of a parametric curve from the set of equations, we will often try to eliminate the parameter. So here we were calling our parameter t, and obtain a Cartesian or rectangular equation. That is something only in terms of x and y, that no longer involves the parameter t. And if we have a Cartesian equation, we might recognize it as the graph of some function or a familiar curve. So to see how that would work, let's look at some examples. So in this example, we are told to eliminate the parameter for the given plane curves given by the parametric equations and describe the resulting graph. So in part A, we have the parametric equations x is equal to 3 minus t and y is 2t minus 3. So in order to eliminate the parameter t, we can try to solve one of our equations for t. So in this first example, part A, we have x is equal to 3 minus t. So if we were to solve for t, say add t to both sides and subtract x from both sides, we would have t is equal to 3 minus x. And once I have t defined in terms of x, I can take this expression for t and substitute it into my equation for y. So here, y, we were told, is equal to 2t minus 3, but we just said that t is equal to 3 minus x. So y is then equal to 2 times 3 minus x minus 3. And simplifying, we have y is equal to 6 minus 2x minus 3, or y is 3 minus 2x. So what we're left with is an equation involving only the variables x and y. So we have eliminated the parameter t. And what we're left with is a Cartesian equation, or a rectangular equation, which we recognize as a linear function. So the curve, the parametric curve described by these equations, would be a line. So here we have a line. If we want to be a little more specific, we can say a line with slope -2 and y-intercept 3. So this first example illustrates that if we're able to solve one of our equations for t, we can then substitute that expression for t into the other parametric equation and try to get a rectangular equation, which we're a little more familiar with when we are thinking about graphs. So let's look at another one. In part B, we have x is 3t plus 1, and y is t squared minus 4. So as with part A, if we solve the first parametric equation for x, we have x minus 1 is equal to 3t, or dividing by 3, x minus 1 all over 3 is equal to t. So once I have t in terms of x, I can take that expression and substitute into my equation for y, and we have y is t squared, so here x minus 1 all over 3, quantity squared, minus 4. Or simplifying this a little bit, this is the same as x minus 1 squared divided by 3 squared, or multiplying by 1/9 minus 4. So we recognize this now as a quadratic equation involving only the variables x and y. So we've eliminated our parameter to get this Cartesian or rectangular equation. And we know that the graph of any quadratic is a parabola. So here we have a parabola. And if we want to be a little more descriptive here, this is written in the standard form for the equation of a parabola. So we can see from this equation that its vertex is at 1, -4, and it's opening upward. All right. So we see in these first two examples, parts A and B, that we have a way to eliminate our parameter t and get a Cartesian equation whose graph we may recognize. So let's look at another example that might be a little bit trickier and illustrate something that we want to be a little careful about. when we're working with parametric curves. In part C, we have the parametric equations x are equal to 4 minus t, and y is equal to the square root of t. So as with our other examples, to eliminate the parameter, we can try to solve one of our equations for t. So here we have x is equal to 4 minus t. So solving our first equation for t, we have t is equal to 4 minus x. And then I can take that and substitute it into my equation for y. Y was the square root of t, but t is equal to 4 minus x. So we have the following equation, which is a rectangular equation for our parametric curve. Here we have the graph of the square root function with some shifts being applied. Another way that we might also go about finding a rectangular equation is by doing the following. So we'll mention, okay, this was one approach, or an alternative approach would be to solve our second equation for t. So here y is the square root of t. So to solve for t, well, we could square both sides. T would be y squared. So our x equation is then 4 minus t, which was equal to y squared. So we have another Cartesian equation relating x and y. We notice that it's equivalent to the first equation that we had. So thinking about the graph of this, well, x is a quadratic function of y. So here we have a part of a parabola opening along the positive x-axis. So we have something that looks like the following. So if y is 0, x is equal to 4, and then we have a parabola opening in this direction. So we would have a curve that looks something like this. Now, one thing that we need to be a little bit careful of here, if we use this second approach where we solve our second equation for t, that is t is equal to y squared, we find that x is 4 minus y squared, which we recognize as the graph of a parabola, just opening along the x-axis instead of the y-axis. However, one thing that we need to be a little bit careful of if we are sketching our curve is recognizing any restrictions on the domain of these parametric equations. So this set of parametric equations does not give us this full parabola that I've illustrated here. Let's think about why not. Well, our equation for y was the square root of t. And in order to have real valued coordinates for x and y, we see that t would have to be non-negative. In particular, our y coordinates, which are the square root of t, well, if t is non-negative, then the square root of t would also be non-negative. So the part of the parabola that we're actually looking at for this equation is just the upper half of this parabola, where y is positive. So we would not include this lower half here. And we see that as t becomes larger, y would get larger and larger, so the orientation of this curve is moving in this direction, with this initial value corresponding to t equals 0, and then as t becomes larger, we're moving along this arc of that parabola. So thinking back to our earlier examples in parts A and B, we'll notice that the parametric equations in parts A and B were polynomial functions of t. So their domain is all real numbers. There was no restriction on that parameter value t. So we would, in parts A and B, be sketching out the entire line and the entire parabola that we were describing, whereas in part C, we have just part of a parabola since we had a restriction on our parameter t. So something to be a little careful of when we're working with these parametric equations. So let's look at some other ones, maybe a little more complicated. So in part D, we have the equations x is equal to 2 cosine t, y is equal to 2 sine t. If we try to use the same approach of eliminating the parameter, well, one way that we could try to do this is by saying, well, x is equal to 2 cosine of t. So solving for t, well, we would have x over 2 is equal to cosine of t. So t could be expressed as arc cosine of x over 2. And then taking that expression for t and substituting into y, we have y is equal to 2 times sine of arc cosine of x over 2. But then the question is, well, what does this graph look like? Well, we have no idea. Certainly, we're not familiar with the graph of sine of arc cosine of x over 2. So this example illustrates that solving for t explicitly and then substituting into another equation may not always be the best approach. So let's think about another way that we could describe the curve given by these parametric equations. So here we have x and y are defined as 2 cosine t and 2 sine of t. So let's think about relationships between these trig functions, sine and cosine, that we're a little more familiar with. And probably the most common relationship among sine and cosine would be the trig identity that the sum of their squares is equal to 1, namely sine squared of x plus cosine squared of x, or any variable must be 1. So instead of using this approach, we saw this was not very effective. So let's try something else here. Trying to make use of the sum of squares here, let's consider taking x squared and y squared. Maybe let me illustrate this individually first. Looking at x squared, we would have 4 times cosine squared of t. And looking at y squared, we have 4 times sine squared of t. So if I want to make use of the trig identity involving the sum of sine squared and cosine squared, well, let's add these two terms. X squared plus y squared is equal to 4 cosine squared t plus 4 times sine squared t. So if we factor out a 4 on the right-hand side, we're left with the sum of cosine squared t and sine squared of t, but we recognize the sum of sine and cosine squared as being equal to 1. So what we're left with is the Cartesian or rectangular equation, x squared plus y squared is equal to 4. In this equation, we recognize as the standard form for the equation of a circle. So here we have a circle with center of 0, 0, or the origin, and radius 2. So recall the standard form for the equation of a circle is x minus x naught squared plus y minus y naught squared is equal to the radius squared, where the point x naught, y naught would be the center of our circle, and r is our radius. So we see that this particular equation represents a circle centered at the origin and of radius 2. So this example in part D illustrates that solving explicitly for t when we're trying to sketch a parametric curve may not always be the best approach. So let's look at another one. In part E, we have the equations x is equal to 3 sine t and y is equal to 2 cosine t, where t is in the interval from 0 to pi. So again, we have these equations involving sine and cosine. So we might try to use an approach similar to what we saw in the previous part D. Now here, if we consider the squares of these values, x squared would be 9 sine squared t, and y squared would be 4 cosine squared t. So if we sum these squares, x squared plus y squared, well, we run into a little trouble here. Because in this example, the coefficient for sine and cosine squared are not equal. Here the values are 9 and 4. So we can't factor out the same number to get just sine squared and cosine squared as we did in part D. So instead, let's do the following. Let's make these coefficients the same by obtaining just sine or just cosine of t without a coefficient in front. So for our first equation, we have x is 3 sine of t. So if I solve for sine of t, well, I would just have to divide both sides by 3. So sine t is x over 3. And our second equation is y equals 2 cosine t. So dividing by 2, we have cosine of t is y over 2. So if I want the sum of sine and cosine squared to make use of the same trig identity that we did in part D, I could square these values and take their sum. So I would have x over 3 squared plus y over 2 squared would then be equal to sine squared t plus cosine squared t. But again, we recognize that the sum of sine squared and cosine squared t is equal to 1. So simplifying a little bit, on the left-hand side, I have x over 3 squared, or x squared over 9, plus y over 2 squared, or y squared over 4, is equal to 1. So at this point, I have a Cartesian equation, only involving x and y, and we recognize this equation as representing an ellipse. So it's like the equation of a circle, but we have different coefficients for our x squared and y squared. So it's a circle that's sort of elongated along one axis, which gives us an ellipse, or sort of an oval shape. So if we want to maybe think about what this curve looks like in the xy plane, let's think about sketching our graph. So here, in general, for this ellipse, one way that we could sketch our graph that I typically like to use is by finding my x and y intercepts. So to get the x-intercept, we would set y equal to 0. So looking at our equation here, if y is equal to 0, then we would have x squared is equal to 9. So x would be plus or minus 3. So our x-intercepts are at positive and negative 3. And to find our y-intercepts, we would set x equal to 0. So in the equation of our ellipse, if x is 0, we have y squared equals 4. So y could be plus or minus 2. So in general, we would have a parametric curve, which is an ellipse, looks something like this. But being a little bit careful, we notice here in part E that we had a specific domain for our t values, namely t is ranging from 0 to pi, so we may not have the entire ellipse, but just some part of it. So let's think about what part of the ellipse this represents. So if t is 0, when we substitute 0 into our parametric equations, we find that x is 0 and y is 2. So this point corresponds to t equals 0. And we want to see which direction we're moving along this ellipse. So as t starts to increase, say from 0 to pi over 2, well, our x value is then increasing. We have 3 sine t, which is initially increasing. So our x values will be getting larger. So we're going to be moving in this direction. And when t is equal to pi over 2, we would have x and y are given by 3 and 0. So we're moving in this direction along our ellipse. Here, this value this point corresponds to t equals pi over 2. And as t continues to increase towards pi, our x value, 3 sine of t, begins to decrease from pi over 2 to pi. And our y value continues to decrease. And when t is equal to pi, we have the point 0, negative 2. So the specific part of the ellipse that these parametric equations represent is that right-hand side traced out in red as I've shown here. All right. So let's look at some other ones. In part F, we have x is sine of t and y is cosecant t, as t is within the interval from negative pi over 2 to pi over 2. So here we no longer have trig functions involving sine and cosine, but sine and cosecant. But we know the relationship between the sine function and the cosecant function. So here we have x is equal to sine of t. Y is cosecant, which is defined as 1 over sine of t. So y is given by 1 over x. So here we have our Cartesian equation. Y is equal to 1 over x, or x times y is equal to 1, which we know the graph of. It looks like a hyperbola. So in general, the graph of 1 over x looks something like this. But again, we see in part F that our values of t are restricted from negative pi over 2 to positive pi over 2. So let's think about what part of this hyperbola we're graphing. So starting with a t value of negative pi over 2, when t is negative pi over 2, sine of negative pi over 2 would be negative 1, in which case y is 1 over x. So we would have y is also negative 1. So I would be looking at the following point on my curve. When t is negative pi over 2, we have the point negative 1, negative 1. And as t starts to increase from negative pi over 2 towards 0, well, sine of t is then increasing towards 0. So x is increasing. We're moving from left to right. And as x is closing in on 0, y, which is 1 over x, starts to become infinitely large, but in the negative direction, since our x values are still negative. Now, as t starts to move from 0 to pi over 2, we see that we move to the other side of this vertical asymptote. And when t is equal to pi over 2, x, which would be sine of t, would be 1. And then our y value, 1 over x, would also be 1. So we're not drawing a scale here, but start moving towards this point where t is equal to pi over 2. So we have a portion of our hyperbola which is traversed in the direction shown, and here the midpoint of our interval when t is equal to 0, well, we know sine of 0 would be 0, so our y value would then be undefined, so we're seeing this vertical asymptote which corresponds to a parameter value of 0. Okay. So let's look at another one. In part G, we have the equations x is equal to 2 plus cosine t, and y is equal to 1 plus sine t, where t is within the interval from 0 to pi over 2. So in this example, again, we see our equations involving sine and cosine of t. So if we try to make use of the trig identity that the sum of their squares is equal to 1, well, let's first solve for sine and cosine of t using our parametric equations. So in general, any time that your parametric equations involve sine and cosine of the same argument, say sine and cosine of t, you want to solve for sine and cosine and then take the sum of those squares, which we know is equal to 1. We've seen that in part D, part E, and now in part G. Solving our first equation for cosine of t, we have x minus 2 is cosine of t. And solving our second equation for sine, we have y minus 1 is equal to sine t. So squaring both sides of these equations, we would have x minus 2 squared is cosine squared t, and y minus 1 squared is sine squared t. So taking the sum of those squares, we have x minus 2 squared plus y minus 1 squared is equal to cosine squared t plus sine squared t. but we recognize the sum of those squares as being equal to 1. So we have x minus 2 squared plus y minus 1 squared is equal to 1. So this would be our Cartesian equation, or rectangular equation, describing our curve. And we recognize this as the standard form of the equation of a circle with a center of 2, 1, and radius 1. So let's think about sketching our curve here. So we have in the xy plane a circle centered at 2, 1 of radius 1. So something like this. But again, we notice in this example, part G, we have some restriction on the values of our parameter, t. Namely, t can only range from 0 to pi over 2. So we may not have this entire circle, but let's think about what portion of the circle this represents. So when t is equal to 0, we would have an x value of 3 and a y value of 1. So we would be at this point on our circle, 3, 1. And as t starts to increase from 0 to pi over 2, our x values will start to decrease. So we're moving from that initial point towards the left, which doesn't help us too much. We don't know if we're moving clockwise or counterclockwise around this circle just yet. But looking at our y equation, 1 plus sine of t, well, as t starts to increase from 0 towards pi over 2, we know that sine of t will be increasing, so y is increasing, which means that we are moving from our initial point in an upward direction, or an increasing value of y. Now as as t increases towards pi over 2, well, when t is equal to pi over 2, we have an x value of 2 and a y value of 2. So we would be talking about this point 2, when t is equal to pi over 2. So we're talking about just this arc or quarter circle traversed in the direction shown here. All right. So now that we've seen some examples of eliminating the parameter to find the Cartesian equation for a curve, let's consider the problem of moving in the reverse direction. So as we'll see a bit later in this course, it's often useful to take a rectangular or Cartesian equation for a curve and use parametric equations to represent it. And we'll see some nice applications of that later in the course. But this process of finding parametric equations to describe a curve is called parameterization of a curve. So this process, called parameterization of a curve, is where we have a Cartesian equation for some curve, and we want to find a set of parametric equations which describe that curve. So let's look at examples of this. So in this next example, we are told to find two different parameterizations of the graphs of each equation. So let's take a look at this. In part A, we have y is equal to 3x minus 5, which we recognize as the equation of a line, and we want to parameterize this. So In order to do that, well, we need to introduce parametric equations for x and y. Now, in the event that we have a Cartesian equation where y is given by a function of x explicitly, that is, if we can solve for y, one easy parameterization is to let x equal t. Now, if we let x equal to t, then y is equal to 3x minus 5, so that would be 3t minus 5 if we called x t. So this would be one simple parameterization if we ever are able to solve for y explicitly. We can just replace x by t, and then we have the equation for y in terms of t immediately. So this would be one parameterization of that line. Now, another parameterization would be to just manipulate the value of x slightly. I could take x as maybe instead of t, 2 times t, in which case y is equal to 3 times x, which was 2t minus 5. So y would then be 6t minus 5, where x was equal to 2t. So this would be an alternative parameterization. Now, how are these two parameterizations related to one another? Well, they're sketching out the same line here. So let's think about what's happening geometrically. So here we had a line of slope 3, y-intercept negative 5. So in general, just a rough sketch looks something like this. So our parameterization that we have of this line, our first parameterization, where x is t, y is 3t minus 5, well, as t ranges over all real numbers, we're tracing out this entire line. And as t is increasing, x is increasing, and so is y. So we're moving in this direction along our line. So if t is 0 in particular, we have this intercept 0, negative 5. As t increases to 1, we would have x is 1 and y is negative 2. So we would have the following point, t is 1. When t is 2, x is 2, y would be 1. So we would have the following point, and so on. So how does this second parameterization describe the line? Well, as t increases, we're still moving in the same direction along our line, and we're tracing out the entire line as t ranges over all real numbers. But the speed at which we're tracing out this line is increased. So in particular, if t is equal to 0, well, we still have this same point. But now, as t increases to 1, our x value is 2 and our y value is 1. So for the second parameterization, we move from this point to the point 2, 1, but by only increasing t from 0 to 1 instead of from 0 to 2, as in the first parameterization. So these two parameterizations are describing the same line, but maybe traversed more quickly if we increase the coefficient in front of t when we choose x. So here, just a little description of how these two parameterizations would be related. So looking at another one in part B, we have y is equal to x squared plus 2x. So again, any time that we have the Cartesian equation given explicitly as y equals a function of x, an easy parameterization is to let x simply be t, in which case y is equal to x squared, or t squared, plus 2 times x, or 2t. So we have the following parameterization. Or, of course, another parameterization would be to just change the coefficient for t in our choice of x. If x is, for instance, 2t, then y would be x, or 2t squared, plus 2 times x, which was 2t. So simplifying, y is 4t squared plus 4t, and x is then 2t. So we would have the following two parameterizations, which both describe the same parabola here, just traversed in a different, or the same direction, but traversed more rapidly. Okay, so let's look at another example. In part C, we have x squared plus y squared over 4 is equal to 1. We recognize this as representing an ellipse. And here, there's no nice way to solve for y explicitly. So we could solve for y, but we end up having something of the form y is equal to plus or minus the square root of an expression. So it may not be as easy to parameterize as in parts A or B. But we can think back to our previous example, and we saw that parametric equations for an ellipse might involve sine t and cosine of t, because we know the sum of those squares would be equal to 1. And here, the equation of our ellipse is involving the sum of two terms squared. In particular, we have x squared and y squared over 4 we can think of as y over 2 quantity squared being equal to 1. So if we want to parameterize this, let's think about maybe rewriting this as the sum of two terms squared is equal to 1, maybe sine and cosine of t. So one choice for a parameterization for this ellipse would be to take x as sine of t, and then y over 2 as cosine of t. So here we could let x equal sine t and y over 2 equal cosine of t, or solving for y would be 2 times cosine t. So this would be one parameterization. Or we could reverse our choice for sine and cosine here. So we could also use, for instance, x is equal to cosine of t, and y is equal to 2 sine t. Just reverse which one we call sine or cosine, because the sum of the squares would still be 1. Or, of course, there's alternative choices here. We could let x be, for instance, sine of 2t, and y be 2 cosine of 2t. So even if we change the argument of sine or cosine, say from t to 2t, the sum of the squares would still be 1. So we can see from these few examples of finding a parameterization of a curve that there are infinitely many parameterizations possible for a given curve, because we could always replace t with, say, 2t or negative t, something like that. We would have the same parameterization, maybe just traversing the curve more quickly, or in the opposite direction. So our last example for this section illustrates one application of parametric curves, maybe in tracking the motion of some object through the plane or through 2 dimensions over time. So in this last example, we're told that an object is moving along a curve defined by the equations x is equal to t minus 1 and y is equal to t squared minus 2t. So given that information in part A, we are asked to find the position of this object at time 3. So if t is equal to 3, then of course we can find the position of our object using these equations for x and y. X is t minus 1, so x would be 2, and y is t squared minus 2t, so that would be 9 minus 6, or 3. So our object is at the point 2, 3 in the plane. All right. Now in part B, we ask the question, at what time does the object pass through a given point? So one application here, if we know the equations describing the path of our object, we can ask at what time it will pass through a given point, as long as we know it passes through that point. So in order to determine the time at which our object passes through the point 415, well, this point gives us our x and y coordinates. So using the parametric equations for x and y, we have x is t minus 1, which we're going to set equal to 4, the x coordinate given in our point, and y, which is t squared minus 2t, we're going to set equal to 15. And we want to solve for t here. Now we could solve either equation for t, and it looks like certainly the first equation involving x is easier to solve. If I simply add 1 to both sides, I have t is equal to 5. And looking at our second equation, t squared minus 2t minus 15 equals to 0. Well, this can be factored as t minus 5 times t plus 3 is 0. So we had 2 choices, either t was 5 or negative 3. So the only value of t that satisfies both of these equations is the first value, t equals 5. Now we could have also, once we solved that first equation for t, we saw there was only one solution, t equals 5. We could have then maybe just substituted 5 into the second equation and seen that it does indeed hold. So at time 5, we would have our object passing through this point. So maybe say after 5 seconds or 5 minutes, maybe 5 hours. We're not given the unit for time here, but we have the value of t for which our object is passing through this point. So in part C, we ask the question, well, does the object pass through a given point, say 639, and then justify our answer? So similar to what we did in part B, to see if our object passes through this point, we're going to take these coordinates as our x and y values and see whether they satisfy these set of parametric equations. So we're going to take x, which is t minus 1, and set it equal to 6. And we're going to take y, which was t squared minus 2t, and set it equal to 39. So solving our first equation for t, we find that t would have to be 7. And if we substitute 7 into this second equation, we would have y is equal to 7 squared, or 49, minus 2 times 7, or 14, which would be equal to 35. It is not equal to 39. So there is no value of t that would satisfy both of these equations. So there is no time at which the object will pass through that indicated point. So here, to answer our question, we can say no, the object does not pass through the point 639. There is no value of t satisfying these equations. Well, that would be our justification for why the object does not pass through that indicated point. So in the last part of our example, we're asked to find a Cartesian equation for the path of this object. So if we want to describe the path that our object is traveling, well, we could eliminate the parameter. So here, our first equation was x equals to t minus 1, and our second equation was y is t squared minus 2t. So solving the first equation for t, we have t is equal to x plus 1. Let's add 1 to both sides. And then substituting that expression into our equation for y, we have t squared, or x plus 1 squared, minus 2 times t, which was x plus 1. So simplifying a little bit, we have x squared plus 2x plus 1, and then minus 2x minus 2. So y is then x squared minus 1. So we have a parabola for the path, or the curve, which describes the path of our object through the plane. Okay. So in this section, we've introduced the concept of a parametric curve or parametric equations. We've seen a couple of ways to sketch the graph of parametric curves, either by choosing specific values for t and substituting into the equations and plotting the points, or by eliminating the parameter. And we've also seen how to take a Cartesian equation and find a parameterization for the graph of that equation. Now, one thing that I'll finish this section with is an illustration of using some software to sketch parametric curves. So in certain cases, we might have really messy parametric equations where it's not possible to eliminate the parameter, and it may not be easy to choose specific values of t to evaluate the functions. So we can always make use of software to sketch parametric curves in the plane. So to illustrate this, let me pull up my browser here. There's a free program which you can access online called, the site is called Desmos. And they've got a lot of nice graphing utilities. So in order to plot parametric equations, we can make use of Desmos. So here you might try, just in your favorite search engine, search for Desmos plot parametric equation. And there's a few different links here. I believe this second one will take you directly to the plotting tool. And so to illustrate how this works, let's say that we can plot individual points. So it shows us here how to plot a point 2, 3, which of course is shown in green here in our plane. And then we might want to plot some parametric equation or parametric curve. So in order to do that, we can just input the parametric equations x of t and y of t as an ordered pair, as shown here. And then we might specify a domain. So we see, for instance, if we had the parametric equations, x is sine of 7 pi t, and y is cosine of 5 pi t, as t ranges from 0 to 2, we have this very complex curve sketched out. So it may not always be possible to eliminate the parameter and express the curve in terms of x and y easily. So if we wanted to plot a different curve, just to illustrate how this works, you can just change your functions here. So let me edit my x and y functions. So we could take, for instance, maybe as x to be, let's say just t, and then y we could take as maybe t squared. Well, as t ranges from 0 to 2, of course, we see, well, y is equal to x squared, so we have this arc of a parabola. And if we want to specify a certain part of our parabola, we can edit the domain for t. So let's say as t ranges from -3 to +2, we would have this segment of our parabola. So the graph updates based off of your input. So this is one way that we can always sketch parametric curves without having to eliminate the parameter. So you can make use of this utility throughout the semester to check your work or to see what exactly a parametric curve looks like, or to plot some maybe complex parametric equations that would arise later in